clear about what, as a geophysicist, we mean by physical properties. And the reason that this is so important is that your use of geophysics will be a twofold. You recognize your problem, and you have to translate that problem into geophysical physical properties. So you have to transfer your problem into these physical properties. Once we've done that, then the geophysicist is like, okay, I got it. I know what to do, and here I'm going to do survey and stuff like that. But this is the crucial moment. So it's extremely important. Okay, so we talked about some relevant problems last time. We'll do about forces, natural hazards, geotechnical engineering, environmental problems, and subsurface or surface storage. And the idea is that they all require, in trying to solve these problems, some way of trying to view into the Earth without actually directly sampling. And that is the realm of geophysics. So here's how a geophysical survey works. We need to have a source. So we need to somehow put energy into the Earth. And then inside here is going to characterize a number of physical properties. And we're going to talk about each of them. And then depending upon what those physical properties is, then we're going to get some response and measurement data. So those are the three parts. We've got a source, we've got the Earth, and we've got data. And what we ultimately want to do is have a problem here that's connected with these, with the Earth. We're going to set up the source, measure some data, and try to infer something about what's going on here. So the question then is, okay, which properties are we talking about, and how do they connect with my particular application? So if we think about physical properties from a geophysical perspective, these are the things that we're talking about. And I'm not sure how many of these would be in your lexicon, but there's density. We're going to talk about each of these in detail, so I'm not going to say very much about density, kind of related to how heavy something is. Magnetic susceptibility, that's the ease with which something can become magnetized under the application of an external field. Electrical conductivity tells you something about how easy it is to pass electrical current through something. Chargeability, for anybody who has been connected with an induced polarization experiment, or IP, what this is, it's actually this phenomenon that the Earth can actually act like a capacitor. Kind of interesting. Electrical permittivity, this is what's happening, the ease with which something can become polarized under the application of the electric field. And elastic moduli. I would guess that the bulk of the engineers here are very, very familiar with elastic moduli and compressibility and shear modulus. The reason why this is important is the following. If I take anything, I take this desk, right? I have many ways of describing this desk. Geologists might describe it as, oh, it's got a shiny surface, it's hard, it doesn't scratch. I guess you guys can lick things too. I'm not kidding. But so that's a description. Okay. A geophysicist would look at this and say, oh, how dense is it? How much is it weight per unit volume? Or how easy can I pass electrical current through that? And if I knew all of those physical properties, it's kind of like having a fingerprint. So if I know all the physical properties about this object, I actually know what this object is. So that's how we characterize the thing. Our physical properties kind of combine to give us a fingerprint of what's there, and then that's how we determine that, yeah, this thing is dense. So let's just look at a couple of these. So here's density. You're probably all familiar with this. So density is the mass per unit volume. And it's got units, either grams per cc or kilograms per cubic meter. And there are certain things that have a low density, like wood, or a high density, like gold. So if we look at the density of Earth materials, they actually vary quite a bit. So if we work in grams per cc, air has really got a low density. Water is the calibration mark, so 1 gram per cc. And then other things, various kinds of rocks, and that will have much larger density. So perhaps a question you might ask as a geological engineer is, okay, I've got sedimentary rocks, and I've got, maybe igneous rocks or some other kind. Like, why does the density vary? I mean, why does a sedimentary rock have a lot lower density than other types of rocks? I don't know. Yeah.
Pore spaces.
Perfect. Yeah. So we've got rocks that have pore spaces. So here's a rock. If you look at it, it's got pores. It could be filled with fluid, but fluid is generally low density, or it could even be air filled. Compared to something that doesn't have that porosity. So this rock will be a lot more. This rock is going to be a lot less dense than something. The other thing about density is that, as you might imagine, it increases with pressure. You compact. You think about spaces in sands or rocks. As you compact it, you get rid of the air voids, and so you have unconsolidated material up here and consolidated material down here, and so you're going to have a low density and then a high density. If you go down to larger scales in here, so here's depth in kilometers. This is like 60 kilometers down here, and the general kind of crustal depths or densities, maybe 2.5, but by the time you get down to upper mantle, you start to get to 3.5. The other thing about density is that it varies with pressure, as we said, and can actually get quite large. So if you look at an Earth scale, so the upper regions here on the crust, they're sort of like 2.2 grams per cc. But actually, by the time you get down to the inner core, the stuff is really dense. It's like 13 grams per cc. That's just because of all of the pressure, the changes that are happening to make this stuff very dense. So if you took a balloon, for instance, up at the surface, it would have this sort of size here. As you put that balloon, deeper and deeper into the Earth, it's just going to occupy a much smaller. So in general, if you look at the composition, you've got ultramafic rocks here, so they're dark and got high silicon. And as you go to lighter rocks, more felsic, you end up with lower density. So you've got a suite of densities for particular kinds of rocks. So how is that used in geophysics? Well, suppose that you've got a cavity someplace. So this has got a really low density. It's filled with air, or maybe even if it's filled with water, it's still going to have a low density. And so if you took some kind of instrument that somehow measure the gravitational attraction over here, you walk over, you have a low value here, high values up there. Or something like got mineralization high veins of very dense material, again, you'd now have something that maybe has got a high value over top of it. So that's kind of the idea. You get a relationship between this physical property density and maybe, a geophysical curve that goes over here, and how that relates to what it is. Elastic moduli. So here's the here's the Earth. There was an earthquake in China, and it radiates waves outwards. So this is a radiation pattern. This thing here is called a seismogram, and it's got a number of arrivals that come on. There's something called a P wave, S wave, surface waves. These are just ways in which the Earth shakes when something happens. And there's a number of different kinds of waves. There's something called body waves. So here's it's a pressure wave that's moving through the Earth. Effectively, Earth rocks act like a little elastic springs in a way. That's why they're called elastic moduli. So this is a P wave that's coming through. Then you can have shear wave, so it's operating in a different directions. The wave motions in one direction, particles in a different one. And what we're really interested in is the velocities of these waves. And this P wave velocity depends upon the bulk modulus and the shear modulus of this. So this is probably perhaps an equation that you would have seen. So the bulk modulus tells you how much something changes in volume when you change the pressure. And the shear wave velocity just depends upon the shear modulus and the density. So rigidity, shear modulus. So here is the physical properties that we're interested in. These are elastic parameters, but they come into play, and they're important because of how they interact and tell you about how fast a wave, a particular wave, is going to travel through the Earth. We also have surface waves. So we got waves that kind of go on the surface, and that's called a Rayleigh wave. And then there's a Love wave. So again, it's a wave that's on the surface, but it's the particle motion is different. And so we've got these different waves, but they all depend upon these different physical properties. The bulk susceptibility, shear modulus, and the density, but they just combine in different ways to give different kinds of waves that travel at different speeds. So the question is, why don't we just have to worry about trying to get these elastic parameters? And if we knew the elastic parameters, would that actually be completely diagnostic? That kind of relates to what I've said before. The answer to that question is that things are actually complicated. If I look at the P wave velocity of something, then I find that it can vary. So each dry sand, for instance, could go from 400 to 1200, or go from 22 to 27. So if I am just looking at the velocities, I'm actually finding quite a range of velocities that are associated with each one of these. So I can't easily, the thing that I'm going to be measuring are velocities of something, but because I know the velocities, I don't exactly know what physical properties are. And also I find that each velocity could correspond. Like this particular velocity here could be a sandstone or it could be a mudstone. You can't really quite distinguish them exactly. But there are certain things that happen. Certainly fluids have no shear modulus that's attached to it, and that the velocities of all of these different elements are going to depend upon the porosity, the clay content, and action, and vegetation. As a function of depth, velocity generally increases. So if we could go in the upper crust, we've got a couple of kilometers per second. Again, by the time, these were let me rewind. So here was the density as a function of depth, and we had these particular P wave velocities. So if we think about a wave propagating through that is more dense, it might actually propagate faster. That would be sort of a natural consequence, I think. But in fact, the velocity does increase as you go down into the Earth. But if you look at the formula, you find that, oh, it's kind of counterintuitive because we're dividing by the density up here. So if I had a higher density, I think I should have a lower velocity. The point about this is that even though the velocity might generally increase with density, you've always got these other properties that are coming in that are also affecting. But generally, velocity is going to increase with depth. So here's a particular case. This is right at the surface here, and as we're going in here, this is P wave velocity. So low values are in red and high values are in blue, and that's what it looks like. And the high values actually are going to be associated with rock rigidity, and that's where you're going to have increased stiffness here compared to the low velocity. So here's just, this again, something that resonates with the geological engineers, because you're worried about stiffness and rigidity, and there's a general relationship here between velocities and that. An experiment in geophysics is often called seismic tomography, where we take a source. This one's done on the ocean. This is characteristic of hydrocarbon exploration. We've got a boat up here. It's setting off a source, and those acoustic waves go down. They reflect off of substratum down here, and then they come back and are measured at receivers. So by working with these kinds of scenarios, you can try to find what the velocity structure is of the subsurface, and also what the lithospheric structure is. Here's an image of seismic tomography. Here's some seismic section in here, and these are higher velocities in here, lower velocities. And you can see that there's some structure that's perhaps coming in. There's some fault zones in here. There's some layering in here. So the fact that you've got waves coming down, traveling straight speed, coming back up, use that as a picture and gives you some idea about what perhaps what might be. Magnetic susceptibility. Rocks, many of them have all rocks can act like little intrinsic magnets. And so you can have a rock and it can have sort of what are called magnetic domains on them. And initially, that rock might be unmagnetized, so that there's no net magnetic moment that's associated with them. But if you apply a magnetic field, then these guys all kind of line up. This is actually going to be the first physical property that we're going to look at magnetic. So they're going to line up, and then they're going to give their own magnetic. Common rocks have a real wide range of magnetic susceptibility. What we're looking on here is the magnetic susceptibility. This is in a log scale. So this is 10 to the minus 5, and this is 1. So that's 5 orders of magnitude. And then if you look at a particular rock unit, let's suppose you've got a region of rocks in here, sort of mafic, igneous rocks. You can see they have a broad band of magnetic susceptibility. Rocks up here, which have a very higher magnetic susceptibility, usually have a lot of magnetite. That magnetite is a mineral that's highly susceptible, and generally the overall magnetic response of a lot of materials simply depend upon the amount of magnetite that's in them. But I think the point about this is that rocks that you ordinarily deal with can actually have a wide range of magnetic susceptibilities, and those susceptibilities vary over many orders of magnitude. Yeah, so there's, in general, you've got sort of mineral composition rocks, so it could be all of these different iron, titanium oxides, and igneous rocks or metamorphic rocks have a much bigger susceptibility than sedimentary. Mafic, much bigger than felsic, and mineralized, much bigger than country rocks. So there's certain qualitative relationships, but what we'd really like to do is to be able to do some kind of a survey and find out a little bit more about what the susceptibilities are, particular units in here, and then make some geologic improvement. So how does the magnetic exploration method work? Well, initially we've got stuff that's just in, kind of scattered around. You can imagine little pieces of rock that's got a whole bunch of little magnets inside. And then those give rise to their own little magnetic field. And we'll talk about this in detail starting next week. We apply an Earth's field to this, and we're going to make those little magnets line up. And that's going to give rise to a magnetized body. So that's one of the bases of doing mineral exploration. It's also very useful for just general structure. So here's an example of rocks that have been magnetized. So here's geophysical data that's obtained, and those are inverted to give rise to a three-dimensional distribution of susceptibility. So what you're looking at here, it's a result of inversion, which is taking the Earth and divide it up into a whole bunch of little prisms. And then you find out what the magnetic susceptibility is for each of those that reproduces these data. And then plotting those things up as an isoscope, so you have a threshold, so that everything that's lower susceptibility than some particular value is transparent. And so now you start to see the shape of a body that looks like this. And so this is indicating where that susceptibility is. And actually, in this case, the mineralized body is sitting up. This is actually an example. It's one of my next graduate students here is working. These are all magnetic sensors. They're walking over this region in Montana, and they're looking for this ordnance item. So this ordnance item is made of steel, so there where it's very magnetic, so it has its own magnetic field that's associated with it, and so you can pick it up with these magnetometers, and then at the end of the day, you plot things up, and you get a picture then that looks like this. By the end of next week, you're going to become real familiar with these. The guys here, little elements, these combinations of blues and reds, those are all manifestations of dipole. So just like you, this is the resulting data. You can imagine this is a bar magnet at 7 years. Go ahead and do this survey. The data would actually just look like this. And so what you see here, there's some big guys, there's some little guys, and there's some guys that they're not always pointing that the red is on the north and the blue is on the south. Some of them are reversed. That's actually an indication that this object here is remnantly magnetized. So we see this, and you see, there's a whole bunch of remnantly magnetized objects here. But each one of them looks like a dipole. If I want to go reclaim this land, I'm going to go dig here, dig here, and dig here, dig here. That's a lot better than looking at this field and saying, where to put shelter. Electrical conductivity, ease with which an object or a rock will pass electrical current when there's a voltage that's applied to this. And throughout this course, we're going to talk about electrical conductivity and its reciprocal called resistivity. I think probably most electrical engineers term resistivity might be a bit more familiar. One is just the reciprocal of the other. So resistivity is in ohmmeters and conductivity is in Siemens per meter. So the conductivity of common rocks, interesting now, again, varies by many orders of magnitude. Well, actually, let's look at resistivity. So on these rocks here, going from 0.01, 10 or 100,000. Okay, so that's by 8 orders of magnitude. It's a lot. If we look up here at these rocks that are really resistive, you know, then what have we got? We got igneous, metamorphic rocks, dolomites, limestones, permafrost. Those guys here are really resistive. We try to pass the current through them, they gain very resistive. On the other hand, if you go down to this region, you've got very low resistivities. That means current passes really easy. Things that you got are, you know, massive sulfides and granites and salt water. In between, you got all these other things. You got clays, gravels, tills, just like a whole bunch of stuff. Hydrocarbons, for anybody who's interested in that, is sitting right up here about 100. So again, each kind of rock has got a kind of a broad spectrum of the physical property, and it varies over many orders of magnitude. But it's still quite diagnostic, right? If you see something that's got a resistivity that's this low, you know, like, okay, that is definitely not an igneous rock. One of the big things with electrical conductivity is that much of it is passed through connections of fluids that are inside the rock. So as you like any kind of rock has got a lot of really microscopic channels that got some amount of fluid in, and if you try to pass current through here, that's generally where the current path flows. So there's lots of charge carriers, and they're going to flow through those current paths. How do we measure conductivity? Resistivity. You're going to do this in the lab on Monday. Basically, you're going to put a piece of rock in between two plates, and you're going to put a voltage across here, and that means that you're going to get a current that goes through here. So you measure the voltage drop, you know what the current is, and the relationship of that ratio is called the resistance. And in practice, so you're going to do that in the lab. You've got a field, can't quite have the same geometry, but you do the following thing. You take a generator and you hook it up into two probes, there, and now that establishes a current that's going to go through the earth. Okay? And then you can measure the electric potential between any two other electrodes. So this is what you're going to do in the lab. This is what you're going to do outside. This is what you do. Maybe a question is, okay, so if you took something like this, and let's suppose if you had a region under here that was just a highly conductive body, or maybe a sinkhole that was filled with salt water or something like that, and you measured the voltage, or if you put something like that in here, maybe a sort of question, what do you expect the voltage would be? Would it be higher or lower if you were over conductive body than over? Right. Okay, I'm not going to tell you. You're going to think about that, because you're going to kind of effectively do that in the lab. But you can try to think about, if I have my rock core, that's really kind of conductive versus being something really resistive, then what kind of voltage am I going to affect? So think about that, hit that in the lab. So what about electrical exploration? So we generally have equipment that consists of generators. We've got wires that are being laid out all over the earth. We've got probes that into the ground, and go ahead and measure electrical potentials along the surface. We convert them to what's called an apparent resistivity, and then we get a map. Looks something like that. So in this case here, the blue indicates really low resistivity, so it's conductive, and the red is high resistance. So this is actually a map that, even without knowing the details, it's actually perhaps starting to tell you something geologic, in the sense that, I suppose you're looking for a sinkhole that's filled with water, and you might expect that to have a low resistivity. Water is conductive. And if you're able to follow the blue line here, so kind of coming down like this, then you see like, oh, that may be something that looks like this. Or the other thing you're sometimes looking at from, let's say, a geological engineering perspective is, okay, where's the bedrock? So the bedrock is usually pretty resistant. So in that case, that comes up at this end being more on the red side. So maybe that, that sort of basement bedrock is maybe following something then that looks like. Okay, so that's sort of the idea that ties in, the resistivity with something that you might be interested in. So DC resistivity depends on electric conductivity, but there's another whole suite of geophysical types of surveys which makes use of something called electromagnetic induction. So this is the process by which we have lights. This is the process by which we, put have a time varying current. So let's suppose that we've got a loop wire up here, and we have a current that's changing, and that's going to give rise to a magnetic field that's time varying. And if we have a conductor in here, it's going to generate currents that are in this conductor, and those currents are going to generate magnetic fields that we could measure. So that's a process in which we're starting to see more and more applications now to use electrical conductivity is in these sort of electromagnetic experiments. And the whole basis is really based upon, Faraday's law. Remember that initial experiment, I don't know, 5 or 6, right? And then you have, suppose you're a wire, right? So you just use, and I got a magnet. So I shove the magnet up more into the wire. What happens?
It's current.
You get current and how do you build it? Current going on? Yeah, you put here something at a level, right? So you got a circuit with like a loop of wire. You never do that? No? Serious? Okay. So the wires you do that. The wire, right? And just hook it up to the light bulb, right? Now you take a magnet, you shut it up, right? And then the light bulb comes on, right? So that means that a time varying magnetic field is going to give rise to currents. And then the other principle was that you have a current that drives the magnetic field, right? You did this one, right? Okay, you have a wire, okay, and your current, you put that current, and you have the compass, and it's reflected. So, yeah, so that means that if the current gives rise to a magnetic field. So that's what's happening here. Right? So we have a time-varying magnetic field on something, so that gives rise to currents in here, and then those currents give rise to their own magnetic field. So all that, everything kind of depends upon the electrical conductivity assumption.
Good question. What happens if you go into like somewhere that's like saturated water, like near the wall table? Wouldn't that mess up all the readings? Like, wouldn't that just be like a flat line? Yeah. Because the conductivity would be the same.
Well, you need to have, if you're going to distinguish something, you have a conductivity contrast. So if I'm going to try to find the shape of something, then the shape of that object has a different than what host material. But the fact that you just got, let's say, so uniform water underneath you, you can still do this experiment and find the conductivity of the water. That's not a problem. The other place this is used, this is, I believe this is now used in a lot of these cone penetrometer types of surveys too. So this, you can kind of do resistivity logging, where you take a tool and simply put it down. If this was horizontal, you can just have a tool that's vertical, and you can have a transmitter and receiver that measures data and try to find the electrical resistivity of the region. And then so logging tools are again something that's probably familiar with geologic engineers. And then there's chargeability. So here we could do the same kind of experiment. Put a battery, say 2 probes, put a battery down, and get a current that goes through and measure the electric potential. And the interesting thing is that if the Earth is not chargeable, just like ordinary stuff, we measure a signal that kind of looks like this. So the input waveform looks like this. So this is current. So the current's off, goes on. Stays on for a while, turns off, and then the electric potential that you measured also kind of looks like the same, just has a different amplitude. Okay, so that's the source, that's the data. If the Earth is chargeable, then the little pieces of the Earth actually act like a little microcapacitor. And that means that the charge build up, and the result of that is that the electric potential changes. And so you see this kind of kick here. That actually turns out to be important information. And perhaps all of the techniques in the last 25 years have been important in finding any kind of mineral deposit, especially sulfides. This particular technique has been key. So it's called IP. So there's lots of kind of microscopic explanations to kind of what's going on, kind of depends on how the charges are being moved about, and we'll talk about that as we come. Yeah. But if we look at the chargeability of rocks. Again, it really kind of depends upon the type of minerals and what materials. Groundwater, for instance, no chargeability. Gravels generally have small, alluvium, small. But then if you go to like pyrite, graphite, or chalcopyrite, these will actually have very large chargeability. So if you have those minerals in your ore body, then you'll actually charge part. And again, I'll show you an example when we do this. And this was a mineral deposit that was in northern Australia. This DC resistivity and reduced polarization, they can be done at the same time. So we could take data and you get, we invert those, here's a geologic picture of what's going on. So this is like a three-dimensional inversion of the DC resistivity. It gives us something that's like that. But if we also do the chargeability, then we actually end up with a picture that looks like this. So it's very different. It's very different. So it's like conductivity and chargeability sort of act like two different properties. And this one, which is really a major feature geologically, absolutely major feature, totally worthless from this point of view of economic mineralization. But if we go to the chargeability, this guy here is he's a producing mineralized body. So, and lastly, we have dielectric conductivity. Okay. To a large extent, this is associated with water, and water molecule. If you have a water molecule, it's kind of like a Dielectric kind of spinning around. But if we apply an electric field out of this, then we get these things to line up. And we have effectively, maybe I should put that here. But if we apply an electric field here, then we're going to get a polarization. So it's like these little water molecules here kind of line up. And if I change that electric field, that makes sense for that. Actually, one more examples that people can connect with when we talk about this is your microwave oven. Does anybody know what microwave works? And I'll tell you. Okay, so, but that's the reason that your microwave oven is working and baking your potato has to do with all of this. So, different materials have different relative permittivity. So sometimes called the dielectric constant. And it varies basically between 1 and 80. Air has a value of 1, seawater or fresh water has a value of 80, and other materials are in. But again, it's another physical property. So that what do these units look like? Engineers use these a lot. And the basically self-contained units. Drag them over someplace, and they operate at pretty high frequency, and they end up giving data that looks like seismic data. And here's a picture of what you get with GPR signal. And you can see that there's here's ice up here, and then here's bedrock down here's sediments, and you get a picture. So all of that. Details of the picture coming out because of this dielectric constant and the fact that it's different between the ice and water and bedrock and so forth.
What was that like what was the surface there?
Oh, right here? I have no idea. So that's where we are. So the general geophysical experiment have a source, put some energy in the ground, and we're interested in property. Okay, which one's the first one? Density, second. Susceptibility, third. Good. Yeah. Perfect. Okay, just a sec. So that's how actually came up with all the elastic moduli. So this is our goal, right? We're going to We're going to think about different problems. In fact, I had someone come into my office this morning. She said she worked for a consulting company, and she was supposed to be in charge of deciding what kind of geophysical project to work with, what kind of data to collect. And it was difficult. And the reason it's difficult is you really have to understand your problem in terms of these physical properties. Once you've got that, then you kind of know which survey to choose. So here's what I want you to do for the weekend. If it seems like this course is this front end, it is. But this is a time when you actually have time to do a few things, as opposed to the end of the term. So I'm trying to make this course so that, okay, we're going to starting as much as we can. Let's get a lot of stuff done. We're going to kind of cruise off towards the end when your other projects are coming on. So here's what I want you to do. There's on the GP, there's a section called Foundations. Read it, start to end. And there's going to be a quiz on that. And then there's another thing. There's the team-based learning one. This is a geophysical journey through Ireland. You're now in a position to actually read that because it uses as a base different surveys physical property. So I'd like you to read that, and then you're going to answer individually some TV questions, and you're going to hand those in. But you can do that early, right? So you can download the questions, fill them out, and hand it in. So you've got the weekend, you can do this if somebody. And then what happens next week is that on Monday we're going to have a lecture about the framework. Right, so we now got the idea that we've got this survey of this property. That's fine. We're now going to look at all this framework. Then on Wednesday, we're going to have a quiz on foundations. And then we're also going to have the team-based learning for that. So by then, what you're going to do is you're going to hand in your individual PTLs, and that's going to tell us, like, okay, you read it. And then you're going to get it together as a team and answer this. The lab, you're really going to like because it's on the physical properties. So there's four stations that you're going to measure different physical properties. It's not a computing lab. You're going to be working with electrical magnetic susceptibility, electrical conductivity, sonic velocities, and density. And then on Friday we'll have a lecture on the magnetic. So this will be the Friday will be the first time I'm actually starting one of the 6 surveys. Okay? So you did have a question? Somebody? Okay. No, let's figure out your team by Monday.